So the topic we're looking at now is biomechanics of resistance exercise. So much like the chapter and discussion on structure and function of the body, we're going to be kind of taking a much bigger idea and just kind of looking at some concepts associated with it. So it's important to note biomechanics itself, biomechanics can actually be a major, okay? So it could be an entire course, it could be a major. But we're just going to look at some specific concepts, particularly related to the body. Again, these are things kind of regardless of your area of concentration that will be beneficial to you. So you kind of understand kind of how the body works. So we're going to be looking at the mechanisms through which the components of the body kind of interact to create movement, and the forces involved with it is what we're going to be kind of focusing on here with the biomechanics. So again, we kind of did a pretty at-length breakdown of the structure of the body in the previous section. So the skeletal musculature is a system that enables the skeleton to move. And when you start to look at more in functional anatomy, if you've had functional anatomy or you're just taking it now, you know, one of the biggest things you'll learn about is what's the origin and insertion of all of the muscles. Okay, so a muscle has an origin, which is proximal. It has an insertion that's distal, and it's through the contract. We talked about how a muscle shortens and creates movement. When we further look at kind of how we sort of categorize some of the movement, we have what are called muscles that are agonists to movement, antagonists to movement, and synergists. Okay, so an agonist is the muscle that's creating a movement. So when you look at a movement, the muscle that's actually doing that is your agonist. Okay, so say for instance you go and extend your knee. Okay, you go and straighten your leg out, you extend your knee. The agonist to that would be your quadriceps muscle group. That's the muscle producing the movement. The antagonist would be the muscle that could slow down or stop the movement. So in the case of the knee with extension, okay, the muscle that could slow down or stop the movement would be the hamstring. That would be the antagonist because it does the opposite movement. So the agonist is the muscle that produces the movement. The antagonist is the muscle that could potentially slow down or stop the movement. And we have interactions between our agonist and antagonist when we're looking for movement to help prevent injury and things of that nature. Then you have what's called a synergist. So a synergist is a muscle that assists indirectly with a movement, okay? So when you look at some of the other movements of the body, you have, again, kind of your prime movers or your agonists. Your synergists are going to be the muscles that kind of assist with the movement. The idea is that they help to kind of help to assist, put some strength behind the movement. What you don't want are the synergists to become the prime movers. If the synergists become the prime movers, okay, then you have a situation where, you know, there's likely some weaknesses or a problem with that. So it's really important to make sure that, you know, the synergists are working as such. They're working at muscles that kind of assist and control the movement, that they're not the muscles that are essentially doing the movement for you. If we look at the levers of the musculoskeletal system, so body movements directly involved in sport act through bony levers of the skeleton. So we're going to be talking about levers. This is a concept discussed in biomechanics, and really we use levers every day. You know, day-to-day life we actually use them, but our body consists of them as well. So when you look at what a lever actually is, a lever is a rigid or semi-rigid body that, when subjected to a force whose line of action does not pass through its pivot point, exerts force on any object, impeding its tendency to rotate. So essentially what you're doing is you're producing some type of rotational movement, and the levers, based upon their structure, look to provide some sort of advantage, okay? And we're going to talk about the different classes of levers based upon where the components kind of line up and how they will actually enable some sort of advantage, be it through movement, force production, balance, what have you, okay? So again, this isn't just something that's in the body, it's something that you could actually see in day-to-day life. So when we look here, we have a very simple representation of a lever, okay? And I'll describe what this all means in as far as the different parts, because we're going to end up having three classes of levers, and they're all going to essentially produce different advantages based upon what exactly is they do, and then we'll kind of talk about the body and what that means. So if we look at this, if we look at our different parts here, so you have three basic parts to your lever. You have your fulcrum, okay, that's where it rotates around, okay. You have the lever itself, but there's two parts to the lever. We have two arms basically. You have what's called the moment arm or the force arm. That's the perpendicular distance from where the force is applied to the fulcrum, okay. So this here is essentially our force arm, okay, or our moment arm, okay. Then you have the resistive force, okay, or the resistive arm. That's the perpendicular distance from the fulcrum to where the resistance is taking place, okay. So those are the three main points, and when you're looking at your classes of levers, okay, that's going to tell you the positioning of all of those is going to tell you, first of all, what class lever is it, and then from there you could determine what's called mechanical advantage, which we're going to talk about on the next slide. So, let's just say for simplicity's sake, you were using this lever, this mechanical lever, to kind of lift this weighted ball off the ground. So you were going to push here, okay? So you're going to push down on here to get this ball to go up, okay? So the question would be is, with this setup, do you have a mechanical advantage to make it easier to move the weight of the ball? So that's going to be something we're going to talk about on the next slide, because then what you can do is you can determine based upon that, you could look at the class of lever and you can determine what type of mechanical advantage does it actually provide for you, okay, when you're doing that. And then we'll look at the body and again apply that to the joints of the body, because essentially many of the joints and muscles of the body actually work this way, okay? They work to provide some sort of advantage when you're looking at whether it be movement or applying resistance or force. Okay, so the concept of mechanical advantage, and I'm not so much worried about you being able to calculate, per se, mechanical advantage. I kind of just want you to understand the concept and what it means when you kind of look at the different classes of lever. So it's a ratio of the moment arm through which an applied force acts and to that through which a resistive force acts. So if you remember, we have those two arms, okay? We have our moment arm, okay, or our force arm, and we have our resistance arm, okay? And again, it's the perpendicular distance from the fulcrum that each one of those is measured. If the mechanical advantage is greater than 1, okay, when you do that, so you're basically just measuring the perpendicular distance. If the ratio ends up being greater than 1, that means a person can apply less force than the resistive force to produce an equal amount of torque. Essentially what that means is that if it is greater than 1, you don't have to apply as much force to move whatever it is or create whatever type of movement you're doing. So if we go back and think about that picture, so that picture is actually in your textbook, okay? So if you look at that picture in your textbook and you look at the two arms, okay, and you could just tell by looking at them, look at which one is longer, okay? The moment arm or the resisted arm, okay? So which one of those two is longer? Well, if you look at it, the force arm or the moment arm is longer. It's much longer than the resistive arm. So what that tells you is, in order for you to lift that ball or get that, or basically push down on that lever to get the ball to go up, you don't have to apply as much force to do that. Okay, so say that ball is really heavy. Okay, you don't have to apply as much force because you actually have a mechanical advantage greater than 1. Okay, now if the mechanical advantage is less than 1, okay, or the ratio is less than 1, you have to apply a greater amount of force, and this actually creates a disadvantage. Okay, so say we kind of flipped, say we took, again, looking at that same picture, okay, and it'll just be easier for you to look in your textbook. If you take that same picture, now let's say you just happen to put the ball on the other end. Okay, so now you put it on that longer end. Well, now that longer end now becomes your resistance arm, okay, or it's the moment arm of the resistive force, and your force arm now becomes that shorter part. Well, now in order for you to get that, to be able to lift that ball using that lever, you would now have to apply way more force. You'd actually have to apply more force than what the ball would weigh in order to move it. So that would actually create a disadvantage. Now, we'll talk about what that means as far as some other stuff involved with movement when we look at the body, because interestingly enough, you'll see when we talk about the class of lever in the body and what this means, how our ability to apply force and what that means for our movement, how all that impacts us functionally. Okay, so looking at this picture, you have your three classes of levers. Okay, you have your first class lever, which is right here. Okay, so notice the relationship of the force arm, the resistance arm, and the axis. So if in a first class lever, the axis falls between the force arm and the resisted arm. Okay, so that the lever that we saw on the previous previous slide, and that's in your textbook, that is also a first class lever, because the fulcrum, or the axis, okay, sorry if I use two different terms, but they both mean the same thing. The fulcrum of the axis is between the force arm and the resistance arm. That means that that's a first class lever. Then you have your second class lever. Okay, if we come down here, here's a second class lever. Now what happens is you have your axis or your fulcrum on the end, the resisted arm is in the middle, and the force is at the end. So when you're looking at the length, so if you were to measure the resistance arm and the force arm, again, you have to go back to your definitions. Remember, they're the perpendicular distance away from the axis. So if you were to measure your resisted arm, you would measure from here to here. That's the perpendicular distance. Here's your resistance, okay? You measure from there to there. If you're looking at the force arm, you would measure from here to here, okay? So the definition still stays the same. You're just measuring from the axis to the point of your resistance arm and your force arm. Then you have your third class lever, okay? So your third class lever, now you have, so you still have the axis or the fulcrum on the end. You have your force arm, which is right here. Again, perpendicular distance. Okay, so there's your axis to your force arm. Then your resistance arm would be from the axis to the resistance. Okay, same concept. So in looking at these, it's important to note, so just right away, thinking about what we talked about with mechanical advantage, okay, looking at a first class, second class, and third class lever. In the case of a first class lever, okay, the mechanical advantage could go either way. You can have you could actually have it be at the point where you just have balance, where it zeroes out, okay? Or you could have a mechanical advantage of greater than 1 or a mechanical advantage of less than 1. What that's dependent upon when we're looking at a first class lever is where the axis goes. So if we were to move the axis this way, so say we were to put the axis right here, okay, what do you think that would do to the mechanical advantage? Would that make the mechanical advantage greater than 1 or less than 1? So it actually make the mechanical advantage greater than 1, okay, because you increased the length of the force arm. Okay, if we took the axis and moved it this way, you would now have a mechanical advantage of less than 1 because you've shortened the force arm. You made the resistance arm longer. Okay, so again, it's the same thing as we talked about with that other picture. So the first picture you saw, with the ball on the end was a first-class lever, but the one you saw, it was a mechanical advantage of greater than 1 because of the fact that the force arm, or the moment of the force, was larger. Now, when we look at a second and a third-class lever, okay, so in the case of each one of those levers, in one of them, the mechanical advantage is always greater than 1. In one of them, the mechanical advantage is always less than 1. Okay? So pair those up right now. Think about it for a little bit. Which one would always be greater than 1? Which one would always be less than 1? Okay, so if we look at the second class lever, pause it if you want a little bit more time to think about it, because I'm going to give you the answer. So the second class lever, the mechanical advantage is always greater than 1. In the third class lever, the mechanical advantage is always less than 1. Now think about why that would be, okay? So if you got it right, good for you. If you didn't get it right, let's figure out what you're missing here, okay? The reason why the mechanical advantage of a second class lever is always greater than 1 is because the force arm is always going to be the longer of the two arms. Remember, it's a ratio of the force arm and the resistance arm. So in a second class lever, because of the way it's designed, the mechanical advantage will always be greater than 1. Okay, because if you look at this, regardless what you do with the resistance, say you move the resistance here to this point, the mechanical advantage, you don't have as much of a mechanical advantage, but you still have a mechanical advantage greater than 1. The reason being is that this force arm is still longer, okay? So if we moved our, I'll show you, it'd be a little easier if I draw it. So here, if we put the resistance arm here, okay? Now, here's the length of your resistance arm. Here's the length of your force arm. So you still have a mechanical advantage of greater than 1. Okay? So in a second class lever, that's what you're going to have. In a third class lever, the mechanical advantage is always less than 1 because your force arm is in between the resistance and the axis. So the force arm, again, you can move it, okay? So you'll, again, say we'll do the same thing here. Let's say we move the force arm from here to here. So now this is our new force arm. Okay? So there's our force. Well, the mechanical advantage is still going to be less than 1 because if you're in a third class lever, you're going to be having, there's still your resistance arm, there's your force arm. So your ratio is still going to be less than 1. Okay, so again, when you're looking at that, and again, I'm not going to be so much concerned about you like actually calculating numbers, but you should know that about these levers. Okay, so again, you have to look at that ratio. Okay, so it's the ratio of the moment arm through which the applied force acts to that through which the resistive force acts. If that force arm is bigger, you're going to have a ratio greater than 1. Now, with a first class lever, again, it could kind of go either way. So here's the reason why a first class lever, we sort of talked about it a little bit already. Let's just say that, again, I'll kind of show it this way. Let's do this. If we take, let's just say we shorten this. So say we cut, say this is just, again, we'll just pretend this is like a board on a little rotating axis, okay? We'll cut the board here, and we'll put our resistance here, okay? So what did that just do? So we don't have any of this over here. This is all gone, okay? So what did that just do? That actually increased the mechanical advantage because we have a longer force arm than a resistance arm. Okay, so it's still a first class lever. We've just changed the mechanical advantage. Okay, it's now the advantage is more to force production. Okay, so you actually get to apply less force to move this resistance. Okay, So that resistance now is easier for you to move. If we, if we kept this like this, we push down to get that to go up, there's less force required. Okay? So again, step one in identifying what class of lever you're looking at, okay, is to look at your components. Look at where your axis is. The axis is probably the easiest thing to find. Look at your axis, look at where the force is taking place, look at the resistive force. Okay, look at that first. Once you see how all that lines up, you already know something about what the mechanical advantage is by looking at the distances. So first of all, if you know it's already a second class lever, you know that your mechanical advantage is greater than 1. Okay, if it's a third class lever, it's less than 1. If it's a first class, you do have to look at which, which arm is longer. Okay, and usually you can visually see that. So just make sure you could identify what it is you're looking at to be able to determine what class of lever it is, and then from there you get your mechanical advantage. So now what we want to do is we want to apply this concept to the body, okay? So we have muscles in the body that act through levers. That's going to kind of be our focus. We do have a lot of muscles in the body that don't function through levers, okay? So for instance, some of the muscles in the face, we have muscles in our arteries. They don't function through levers, but when we look at most of our movements, particularly in our appendicular skeleton, much of that is done through the use of levers. Again, it's not a different concept, it's just a different way of looking at it. So now we're just kind of applying that, these pictures that sort of look like the seesaws or the teeter-totters in a playground, to just basically applying that to the body. Okay, so we have an advantage here. Now, sometimes there has to be some context when you're looking at how the muscles operate in the body as far as classifying them as levers. And this will be something that we explore more when we kind of meet face to face and talk about this, because this is a concept that can be a little difficult to understand. So I want you to kind of take your time with it and be able to see, so you're not, there doesn't have to be guesswork here. You can just look at something. As long as you can define those different parts, you can usually make sense as far as what it is that you're looking at with this. So if we look at this picture right now, so remember I said you have to find your force arm, okay, or your moment arm of the force, and you have to find your resistance arm. So we're looking at here is extension of the forearm against resistance. So you're just looking to extend your arm. So when we're looking at this is the tricep muscle right here. You have your elbow joint right here. So we're basically looking to extend. We're basically looking to take our arm and straighten it out. Okay. So we're going to have our force arm. So the force arm is going to, the force is obviously going to come from the muscle. So the force arm looks at where the tendon inserts at to the length of the muscle. You have your force or resistance. Okay, so that's where the force is going to be, right? So let's even make it easier. Pretend they're holding a weight. Okay, they have a weighted ball in their hand here. Okay, or they're holding a dumbbell. So they're holding a dumbbell in their hand and they're going to extend. Okay, so you look at the length of the resistance arm. Again, get your definitions down. Okay. So the distance, the perpendicular distance from the axis, which in this case would be elbow, to where the force is taking place. Okay, so this the entire, or the resistance is taking place. So here's your resistance arm. Okay, here's your force arm. Now when we measure this, okay, and again, you don't have to get yourself too wrapped up with this. So they're basically saying you have the length of your force arm is, they're measuring it here as 5 centimeters. The length of your resistance arm is 40 centimeters. So it actually gives you less. So even though it's a first class lever, okay, so again, remember with a first class lever, it could be that you have a mechanical advantage of greater than 1. You could have one that's less than 1, or you can actually have one where it is one. And typically first-class levers, when they're one, they look to create balance, okay? So you'll either have a lever that favors force, a lever that favors resistance, or one that favors balance with a first-class lever. This one is at a disadvantage because the mechanical advantage is less than 1, okay? Because the distance of the length of the force arm is shorter, okay? So what does this mean for this, okay? So we have to apply more force in order to basically extend this weight, okay? So we're actually at a disadvantage force-wise when we're looking at this. Now, here's the thing with the body. So you're sitting there saying to yourself, well, geez, well, you know, our bodies are at a mechanical disadvantage. In many cases, that will be the case. However, in the case where the mechanical advantage is less than 1, it makes up with it by giving you more ability to move the resistance, meaning that you get greater movement, okay? Now, we have to apply much more force to create the movement, but you get the ability to move more, okay? We'll talk about that more when we discuss third-class levers in the body and what that means, but that's essentially what you're looking at. You're looking at creating more movement with this type of situation. So here we look at a second-class lever, and really for the most part, it's pretty much agreed upon that this is actually the only example of a second-class lever in the body. So where you're getting, so here we're looking at the foot and lower leg, and what we're seeing here is that when you're weight bearing and you go up on your toes, that's really the only good example of a second-class lever. Okay, now again, let's look at this. So here's what we looked at in the previous slide with a second-class lever. This might help to make a little bit more sense of this. So here's your force, here's your resistance, here's your axis. Okay, so force, resistance, axis. Now, you kind of superimpose that here, okay? So we have our axis, okay? We have our resistance, which is kind of represented of basically our body weight, okay? Because again, that's what we're supporting here. And then you have your force here. So this and this are essentially the same thing. You have your axis, you have your resistance, you have your force, okay? So this is the only example of movement in the body where the mechanical advantage becomes greater than 1. Think about why that would be important in this circumstance, okay? So for you to go up on your toes or be in a case when you're in weight bearing and plantar flexion, you have to support all of your body weight. So it's really important that you have a mechanical advantage greater than 1 in order to do that, because you're essentially supporting now all your body weight on this area, okay? Now, what you lose is movement, because if you think about moving from here to here, there's not a whole lot of displacement that occurs, okay? So while you gain force with a second-class lever, you lose the ability to create more displacement or movement, okay? So, because immediately, a lot of times when I ask the question, I didn't start with this, but many times I'll pose the question, well, what class of lever in our body is the most common? You know, I'll explain them, and students, you know, when I say, well, what do you think in our bodies? What do you think we primarily have? The immediate reaction is to say, well, second class, because we have to be able to move things and produce force. If that were the case, we would lose a lot of our movement, okay? We wouldn't be able to move as much. We wouldn't have the large ranges of motion in our body if we were all second-class levers. So yes, we would be able to produce a lot of force, but we wouldn't be able to move, okay? So our body, I'm kind of taking this away from the next section, our body is actually primarily comprised of third-class levers, okay? So this is a third-class lever here. So our body is primarily comprised of third-class levers for the most part. There are some first. Really, the only example of a Second class is the weight-bearing plantar flexion. Okay, so here's an example of a third class lever. So again, if we go back to our seesaw representation, so here's our force, here's our resistance, here's the axis. Okay, so it's a third. All right, so again, your mechanical advantage is always less than 1. So your force arm is here. This is where you're applying your force. Your resistance arm is here. So the mechanical advantage is always less than 1. Now let's look at the elbow flexion with the bicep. So the picture we're looking at here is of the biceps brachii. This is your elbow, okay? Here, I'll do this because it'll make it a little easier to, again, if visually you're sort of looking at this. So I'll draw this here in the same way. So here's your axis, force. Remember, the force is in between the axis and the resistance when you're doing this. And here's your resistance. Okay, so this might be a little, this drawing over here will be easier for you to make the connection here because it's going in the same direction. So the axis, where's the axis? The elbow joint. Okay, your force. Okay, here's the bicep. There's your force arm. Same thing. The resistance, again, perpendicular distance from the axis to the resistance. So here you're looking at, again, your mechanical advantage is going to be less than 1. Now, again, you're sitting there saying, well, geez, our body's at a mechanical disadvantage. From the force production standpoint, that's true, but what you gain is movement. You have this big, large range of motion. If you take your elbow from full extension to full flexion, you have all of that movement that can take place. So while we lose a little bit of the ability to produce force, we gain motion. So in the case of a class 3 lever, while you lose force production, you gain movement. All right, and you can see that here. So I'll make another drawing. So let's just, again, this is kind of rough, but this is on the ground. So this is the ground. This is your little axis. So this is your teeter-totter again. We're going to put it all the way on the end because we're going to make it a third-class lever. Okay, so here's where you're applying your force. So we're going to apply the force this way because we want the resistance to go up, and here's your resistance on the end, your weight or what have you. So it'll take a lot more force to move this, but let's say you have the ability to movement. You can apply enough force to get this off the ground. Look at how much displacement's going to occur. So as this is moving, you're getting much larger displacement than you would with a second-class lever. If this were reversed in a second-class lever, yeah, you'd be able to provide a lot of force, but you wouldn't have as much movement. Okay, so that's why when we look at a lot of the joints in the body and the muscles and how they interact, many of them are third-class levers because, again, we have to be able to move. Now, we make ourselves stronger by, again, you take, this is why we do, like, for instance, resistance exercise. We strengthen muscles through resistance so that they can get stronger and be able to overcome forces. Okay, whether that be through activities of daily living or for people who strength train for performance purposes, they look to gain that advantage. Okay, so we'll talk about some other advantages and mechanical advantages throughout the body. So really kind of look at that lever concept. It's one of the things that are sometimes a little difficult to see. We'll certainly spend some time face-to-face, or if you have questions about it, please, think of some questions, or what I sometimes tell students is look at other joints in the body and see if you can maybe apply based upon movement and whether you're weight bearing or not, what that actually means as far as the levers are concerned. So now we're just going to look at some other ways we kind of get mechanical advantages throughout the body. So our patella, okay, or our, as the layman term would be kneecap, but your patella is actually more than just a little bone that sits in front of your knee. What it actually does is it provides a mechanical advantage to the quadriceps muscle. Okay, so the patella increases mechanical advantage by kind of maintaining the tendon at a distance from the knee's axis of rotation. So we're looking here at the knee joint. Okay, so here's a knee with a patella, here's a knee without a patella. So what the patella actually does is it keeps the tendon away, allowing greater force to be produced. So if you didn't have a patella, that tendon would just sit flat right up against the femur and would sit closer to the knee joint. So your force being produced would be really close to the axis of rotation, whereas here it actually helps to maintain that distance. Okay, so if you didn't have a patella, the absence of it would cause the tendon to fall closer to the knee center of rotation. So what that would do is it would actually shorten your moment arm. Okay, so the muscle force, so obviously we know the quadriceps tendon is going to pull this way, but by keeping that moment arm much longer, it's actually keeping the mechanical advantage better as it kind of moves throughout the range of motion. Okay, so that's another way we kind of see the concept of moment arms and mechanical advantage being applied to the body. All right, here's another way we kind of look at the concept of mechanical advantage and moment arm. Okay, so it still applies to levers, but here we're focused more on the moment arm and the ability to kind of produce force. So another way we kind of look at this is if we look at the elbow, so we're looking at the elbow joint. If you kind of look at the different positions of the elbow joint, okay, so if you look at all of these different pictures, okay, what do you notice as far as the distance from the tendinous insertion of the bicep in its relationship to the elbow joint? As you look at this, okay, coming to this point, don't worry about these two pictures yet, okay? Going from here to gradually flexing the elbow, what do you notice? Okay, the moment arm, or the distance from the tendon line of action, gets bigger. So what does this mean? As you go from here to here, your ability to produce force and create movement actually increases. Okay, so here's your distance here, getting longer. There's where it's at its longest. So when you're at 90 degrees, okay, when the moment arm is shorter, there's less mechanical advantage. So when your elbow is at 90 degrees, you have a much greater mechanical advantage to produce force and movement here. Okay, now as you continue to flex the arm, what do you notice then again happens? Now then again, you notice that the elbow, okay, or that moment arm, as the elbow flexes, now starts to shorten again. So what that means is once you get past that point, now what you're looking at is, again, that mechanical advantage is starting to go back down. Okay, so what that means is that, in the case here where you're looking at the elbow joint, okay, and the amount of weight that's getting moved, as the weight gets lifted, okay, the moment arm that it acts through and the resistive torque is going to change as the horizontal distance from the weight to the elbow changes. Okay, so if we look at this next slide, so as we look at this, okay, so again, it's the elbow and it's kind of going through the range of motion. Okay, as we move through the range of motion, now again, your focus has to be as far as the person's ability to produce force and movement. You have to look at where the tendon inserts to the axis of rotation. Okay, so Here, we already talked about this. When the elbow's at 90 degrees, that's where that moment arm is the longest. The reason why that's important when we're looking at just kind of the body and movement and the ability to provide force. So we already know that most of the skeletal muscles operate at a mechanical disadvantage, okay? Because the elbow is a you know, in the case of the elbow here, we're looking at a class 3 leveler, okay? So it's really important that during like sports and physical activities that the forces in the muscles and tendons are higher than those exerted on objects on the ground or with things we're trying to move. So essentially what we look at here, okay, so if we think about this, where is this weight going to seem the heaviest? Okay, so in all these different points, so here's a point here, point here, point here, point here, and a point here. Where technically is the weight or the resistance arm going to be the longest or essentially be the heaviest? 1, 2, 3, 4, or 5. Well, in the case if we're looking at, again, the definition of what the resistance arm is, okay, it's going to be here because it's the perpendicular distance. So if we look down here, here's the perpendicular distance. Okay, so to move from here to here, okay, isn't going to be as difficult. So we don't need the moment arm of the tendon to be as long to go from here to here. Here, it's at its longest. So what do we need? We need this tendon to be as far away, and that all matches up. So when the resistance is at its longest, or the resistance arm, or the moment of the resistance is at its longest, so is our force moment arm. Okay? At 90 degrees is where the tendon's going to fall the farthest away from the joint, so it matches up with when the resistance is the furthest. So again, as we continue to flex, what we notice is that resistance moment gets shorter. So the tendon doesn't have to be as far away from the joint. Okay? So the further the resistance moment or the resistance arm moves, so does the force moment or the force arm. Okay, so it all matches up. So the body kind of is able to, so even though it's at a mechanical disadvantage, it's able to kind of match up and go along with what goes on as we kind of move through the body. So that tendon's ability to move, to be further away from the axis of rotation creates that better advantage. So looking at skeletal muscle structure, so again, there are some variations in tendon insertion. So we know generally, you know, again, in everybody where these muscles insert at. However, based upon your body structure, there can be some slight variations as far as how far away the tendons are from the joints in individuals. So, you know, your tendinous insertions are where the tendons are attached to the bone, you know, and in some individuals, based upon their body structure, they could be inserted either farther or closer to the joint line in general than in other people. And what we have in a situation where, say, the tendon is inserted farther from the joint center, usually results in the ability to lift heavier weights. It allows you to apply more force. Now, what that does, though, is it results in a loss of speed. Results in a loss of speed in your ability to contract fast. So what this does is this arrangement reduces the muscle's force capability during faster movements. So if you just think about a lot of your different sports and athletic endeavors, when you kind of look at like body structures and things like that, that's what this is basically saying. So again, it's sometimes the saying that the sport picks the person doesn't pick the sport. If you kind of go by that theory, a lot of times people tend to have better success because they're matching kind of their body structure. And again, we're all a little genetically predisposed, you know, as far as athletically based upon our body structure. So, you know, if you take, I guess the best way to look at this would be if you looked at most power lifters, their tendinous insertions are probably farther away from their joint centers. And if you look at the way most of them are built, you can probably
kind of come to that conclusion. And then what that does is it allows them to produce more force. Now, powerlifters, obviously, just because they're so strong, they can be, explosive to a degree, but they don't per se have that kind of explosive ability, say, that like a basketball player would have. Okay, where now maybe the tendons are maybe a little closer to the joint, where they kind of get a little bit more speed. So that could kind of dictate some of your what you can be a little bit more successful with based upon your body type. So here's what we're kind of looking at with this. Okay, so in picture A here, you can see that the tendinous insertion is a little closer to the joint center, where here it's a little further away. So configuration B, what you're looking at right here over on this side, is that it has a larger moment arm and thus has a greater ability for torque for a given muscle for force. However, there's less rotation per unit of muscle contraction, therefore it's a little slower, okay? Whereas over here, the insertion's a little bit closer. However, if you're looking at the range of motion that gets accomplished per unit muscle contraction, you're getting more. So what this is saying is you can get a faster contraction here, you could get a stronger contraction here. Okay, so again, if that's kind of the way their body's kind of structured and designed in general, you could be looking at maybe two individuals who are maybe successful at different sports. This individual will, if again, all things being equal, they're the same weight at every joint, which likely they probably are, they're probably more successful in sports where force development or activities where force development is a little more advantageous. Whereas over here, where speed is a little bit more advantageous, they might be more adept at some of the skills related to that individual activity.